this video, we'll be exploring the graph of the absolute value function. And let's first just graph the parent function of absolute value, which is just f of x equals the absolute value of x. I've plugged in just a couple x values, and we'll get their outputs here. If we plug in -6 into the absolute value, we'll get out a +6. In fact, anytime we plug a number in, we get its positive or 0 output, because an absolute value is how far a number is away from 0. All right, so now we have a couple coordinate points we can plot. So I'm going to go ahead and plot -6, 6 all the way down to 6, 6. This is the parent graph of absolute value. We can see that it makes a V. And the best way to look at absolute value is that it's a positive line here, a slope with a positive line. Here it is a line with a negative slope. It forms this V because our outputs are going to be positive. But also that we can see that it goes right along the diagonal here when we have just a regular absolute value function and it hasn't been made narrow or wider. So let's take a look at some shifting of the absolute value graph, but always remember V for value. Horizontal shifting just means shifting the graph of the parent function either left or right, and that is called a horizontal shift. If we have inside the absolute value x plus h, that actually means we're moving h units left. And if we have inside the absolute value bars x minus h, that actually means we're moving h units right. It does seem backwards from what you would think. So let's take a look at this graph right here, the absolute value of x plus 4. And since we have plus 4, that means the parent graph moves 4 units to the left. So let's quickly sketch the parent graph. All right, we sketched the parent graph. Then this is a shift from the parent graph 4 units to the left. So instead of beginning at 0, 0, I will begin at -4, 0. And then I just move right along the diagonals. And there we have it. So the blue is really the final graph. It really could be the only graph if you don't feel like graphing the original parent function, just regular absolute value. You can just go right into graphing its shift right here in blue. This one I won't graph the original parent graph. We'll just think about it. And in this case, we have the absolute value of x minus 2. Since we have x minus 2, we're going to be moving 2 units to the right from our original parent graph that starts at the origin. So instead of beginning down here, we're going to begin here at 2, 0. We'll begin at 2, 0, and then we follow right along those diagonals, just like the absolute value graph does. And there we go. The next type of shift is a vertical shift, moving up or down. And in this case, the absolute value just contains the x, and then we have a plus k or a minus k on the outside of the absolute value. In this case, we're moving in the y direction, up or down, because these values in here are not close with the x's, so they are moving in the y direction. This one is straightforward like you would think. If it's plus, we move up. If it's minus, we move down. So I have one example here. We have our absolute value parent graph starting at 0, 0 like we've been talking about, and then it's shifted down 3 units. There's the parent graph. Then the entire thing, down 3, instead of being at 0, 0, we'll start at -0, -3. And then move right along the diagonal there. And that is the graph of g of x in blue. These last types of transformations are not just shifting left, right, up, or down. In this case, we can make our graph narrower or wider by putting a multiple out in front of the absolute value. Now, if this multiple is a fraction right between 0 and 1, that's going to make our V wider. And if that multiple out front, that multiplier is greater than 1, then it's going to make our graph narrower. Then, of course, in this example here, we also have a negative out in front. And if we have that negative, that means our graph will get reflected downward over the x-axis. All of our outputs would end up being negative instead. All right, let's take a look at number 4. I graphed the parent function of absolute value already to help us. And then we can see that this k value is 1/2 between 0 and 1. Therefore, our graph's going to end up being wider. Here's how I like to think about this. All of our outputs are now halved. We take half of every output. So down here, when we plugged in 0, we got an output of 0. Half of 0 is still 0. Therefore, this point is still on our new g of x graph. Then here we had an output of 2. Our y value was 2. Well, we want half of that instead. So instead of the output being up here at 2, it should be half of that at 1. So we should have the coordinate point 2, 1, and then negative 2, 1. Since those outputs there were both 2, we took half of them. Then here our output was 4. The y value was 4. Therefore, we take half of that output. So instead it drops down to being 2, since 2 is half of 4. And note, I'm only looking at even outputs because they're just easier to take half of. And then we could do one more. Here we had an output up at 6, and so instead it would be over at 3. 6, 3, and negative 6, 3, and there we go. So the 1/2 out in front, that 1/2 out in front made our graph a little bit wider than the original parent graph. If we take a look at number 5, once again, I have graphed the parent function, regular absolute value of x, and I'm going to ignore this negative first, but the first thing I'm going to do is worry about this 2. All right, so let's just look at the 2, and then we'll do the negative at the end. So 2 is greater than 1. It's going to end up making our graph narrower, but instead, the way we can think about it is all of our outputs will be multiplied by 2. So down at the origin, we had an output of 0, multiplied by 2 is still 0. Here, we had an output of 1 when we plugged in 1. We had an output of 1, so we'll double that, multiplied by 2. We should be up here at 2 now instead to double that output. And when we had an output of 2, it should double and be 4 instead, being multiplied by 2. And then we have room for one more. When we had an output of 3, that should double, be multiplied by 2, and go up to 6. Now that is just this part. So I want to do a final graph of the whole thing, including the negative. The negative is going to reflect our blue graph over the x-axis. So I'm going to flip everything downward. So instead of having the point, well, let's see, we'll start at 0, 0 again, because that's not moving. But instead of having the point 1, 2, that'll get reflected down to 1, negative 2. And then instead of having the point 2, 4, that'll become the point 2, negative 4. We'll have 3, negative 6. And we'll have the same thing on the other side here. So our graph has been made more narrow, and it has been reflected over the x-axis. So our final graph is the black graph there. The last thing we'll do is find the equations for these graphed absolute value functions. And we can see, let's take a look at this first one. We want to find its equation. So we'll start with f of x equals. All right, how did it shift from the original parent function? I graphed the original parent function in orange once again. This graph here is still going along a diagonal. It has not been made any more narrow or wide than the regular parent function. So there's not going to be a number out in front, nor has it been flipped over or reflected. So we know that we're just going to have an x in there. Now we have to determine what kind of shift it was. It looks like it was a shift to the right. It was a shift to the right 3 units. And moving to the right means minus however many we move to the right. So the graph in black has the equation f of x equals the absolute value of x minus 3. Let's take a look at the second graphed absolute value function over here. This one also looks just the same shape as our parent graph. It's moving right along the diagonal, so it hasn't been made more narrow, wide, or been reflected. But instead of starting at 0, 0 like the parent graph, it's been shifted 2 to the right and 3 up. So this one went 2 to the right and 3 up. So it has both shifts. So moving 2 to the right means that we had x minus 2, since that means 2 to the right, and then 3 up means after the absolute value closes, we do plus 3.